Section: Introduction. In this section, we introduce the model architecture of LLaMA-Omni. It consists of a speech encoder, a speech adapter, a large language model, LLM, and a speech decoder. We refer to the user's speech instruction, text response, and speech response as X-S, Y-T, and Y-S, respectively. For the speech encoder, we utilize the encoder from Whisper Large v3. Whisper is a versatile speech recognition model trained on extensive audio data, allowing it to extract meaningful representations from speech. Specifically, for the user's speech instruction X-S, the encoded speech representation is denoted as H, which is a sequence of speech representations. We keep the parameters of the speech encoder fixed during the entire training process. Next, to help the LLM understand the input speech, we introduce a trainable speech adapter, A. This adapter maps the speech representations into the LLM's embedding space. It first reduces the sequence length by downsampling the speech representations H, combining every K consecutive frames along the feature dimension. Then, H is processed through a two-layer perceptron with ReLU activation, resulting in the final speech representation S for the LLM. We use LLaMA 3.1 to 8b Instruct, which is currently the leading open-source LLM known for its strong reasoning abilities and alignment with human preferences. We fill the speech representation sequence S into a designated position in a prompt template, and then input the entire sequence into the LLM. Finally, the LLM generates the text response Y-T directly based on the speech instruction, using cross-entropy loss for training. Section Summary. In this section, we introduce LLaMA-Omni, a novel model architecture designed for low latency and high-quality speech interaction with large language models, LLMs. It integrates a speech encoder, a speech adapter, an LLM, and a streaming speech decoder, allowing direct generation of text and speech responses from user speech instructions while significantly reducing training data and computational resource requirements. Section: Speech Decoder. In this section, we describe our speech decoder. For the speech response, we first convert the speech into discrete units. We utilize a pre-trained Hubert model to obtain continuous speech representations, which we then transform into discrete cluster indices using a K-means model. We merge consecutive identical indices into single units, resulting in a sequence of discrete units. These units can be turned into waveforms with a unit-based vocoder. To generate speech responses alongside text responses, we add a streaming speech decoder after the language model. This decoder consists of several transformer layers similar to LLaMA, each with a causal self-attention module and a feed-forward network. It operates in a non-autoregressive manner, taking the output hidden states from the language model to produce the discrete unit sequence for the speech response. We denote the output hidden states related to the text response as a sequence. We first upsample each hidden state into chunks, creating an upsampled hidden state sequence. This sequence is then input into the speech decoder, producing an output hidden state sequence. We align this output with the discrete unit sequence using connectionist temporal classification, CTC, which includes a special blank token to extend the output space. CTC helps model the variable length mapping between input and output by merging consecutive repeated tokens and removing blank tokens. During training, we use a two-stage strategy for LLaMA-Omni. In the first stage, we train the model to generate text responses from speech instructions, keeping the speech encoder frozen. In the second stage, we focus on generating speech responses, freezing the speech encoder, adapter, and language model while training only the speech decoder. During inference, the language model generates text responses based on speech instructions. As the model generates text, the corresponding upsampled hidden states are fed into the speech decoder to create a partial alignment, which gives us the discrete units for the generated text prefix. When the number of generated units reaches a set chunk size, we input this segment into the vocoder to synthesize a speech segment, allowing users to hear the response without waiting for the full text to be generated. This approach ensures low response latency, unaffected by text length. The algorithm outlines this process, and since our speech decoder uses non-autoregressive modeling, the alignment for each text token is generated in parallel, maintaining a similar decoding speed for both text and speech generation. Section Summary. In this section, we describe our speech decoder, which converts speech into discrete units using a pre-trained Hubert model and k-means clustering, and generates speech responses in parallel with text responses through a non-autoregressive transformer-based architecture. We implement a two-stage training strategy, first focusing on text response generation and then on training the speech decoder, allowing for low-latency speech synthesis that begins as soon as a predefined number of units are generated. Section. Construction of speech instruction data. Instructs 2S200K. In this section, we describe how we constructed the speech instruction data, known as Instructs 2S200K. To train LLaMA-Omni, we require triplet data that includes speech instructions, text responses, and speech responses. However, most available instruction data is in text format. First, we rewrite the text instructions to better fit speech input. We follow these rules. 1. We add filler words like hey and to mimic natural speech. 2. We convert symbols, such as numbers, into their spoken equivalents for accurate text-to-speech synthesis. 3. We keep the instructions brief and avoid unnecessary words. We utilize the LLaMA 3-70B instruct model for this rewriting process. Next, we generate responses for the speech instructions. Text responses are often too long and complex for speech, so we apply these rules. 1. We exclude any content that cannot be synthesized by the text-to-speech model, like lists or parentheses. 2. We ensure the responses are concise and direct. Again, we use the LLaMA 3-70B instruct model for this task. After we have the suitable instructions and responses, we convert them into speech using text-to-speech models. For the instructions, we use the COSYVOICE 300 MSFT model, randomly selecting a male or female voice for each one. For the responses, we apply the VITS model trained on the LJ speech dataset to create a standard voice. We gather around 50,000 instructions from the Alpaca dataset and about 150,000 from the UltraChat dataset, focusing on the first 150,000 entries. This process results in a total of 200,000 speech instruction data, which we call Instructs 2S200K. For our experiments, we use the Instructs 2S200K dataset for training. We extract discrete units for the target speech using a pre-trained k-means quantizer that has identified 1,000 clusters from Hubert features. We then synthesize these units into waveforms with the hi-fi GAN vocoder. For evaluation, we select two subsets from Alpaca Eval, removing math and code-related questions, resulting in 199 instructions. We synthesize these into speech using the COSYVOICE 300 MSFT model, referring to this test set as Instructs 2S Eval. In terms of model configuration, we use the encoder from Whisper Large v3 as our speech encoder and LLaMA 3.1 to 8B Instruct as our language model. The speech adapter downsamples the speech representations by 5 times. The speech decoder consists of 2 transformer layers similar to LLaMA, with specific dimensions and a total of 425 million parameters. We set the upsample factor to 25 and the minimum unit chunk size to infinity, meaning we wait for the entire sequence to be generated before synthesizing speech. In future experiments, we will explore how adjusting this chunk size affects response latency and the balance between latency and speech quality. Finally, LLaMA-Omni undergoes a 2-stage training process. In the first stage, we train the speech adapter and the language model with a batch size of 32 for 3 epochs, using a cosine learning rate scheduler. In the second stage, we train the speech decoder with the same batch size and learning rate schedule, but with a higher peak learning rate. The entire training takes about 65 hours on 4 NVIDIA L40 GPS. Section Summary. In this section, we describe the construction of the Instructs 2S200K dataset, which involves rewriting text instructions for natural speech, generating concise speech responses, and synthesizing them using TTS models, ultimately resulting in 200K speech instruction data. We also outline our training process for LLaMA-Omni, which includes a two-stage training approach for the speech adapter and decoder, taking approximately 65 hours on 4 NVIDIA L40 GPUs. Section: Evaluation. In this section, we evaluate LLaMA-Omni's performance in generating both text and speech responses based on speech instructions. We focus on two tasks: speech-to-text instruction following, S2TIF, and speech-to-speech instruction following, S2SIF, using a greedy search method for consistent results. To assess how well the model follows speech instructions, we employ GPT-4o to score its responses. For the S2TIF task, we score based on the transcribed text of the speech instructions and the model's text response. For S2SIF, we first convert the model's speech responses to text using the Whisper Large v3 model and then score it similarly. GPT-4o evaluates responses on content, which checks if the model addresses the user's instruction, and style, which looks at the appropriateness of the response for speech interactions. More details are available in the appendix. Next, we examine the alignment between text and speech responses by transcribing the speech responses into text and calculating the word error rate, WER, and character error rate, CER. We label these metrics as OSER WER and OSER CER. For speech quality, we use a mean opinion score, MOS, prediction model called UTMOS to assess the naturalness of the generated speech, referred to as the UTMOS score. Response latency is another important metric, measuring the time from when a speech instruction is given to when the speech response starts. We also track the number of words generated in the text response when the speech response begins, which we call the hashtag lagging word. We compare our model against baseline systems. SpeechGPT is a speech-language model that handles both speech input and output, using a chain of modality prompting method for decoding. SALMONN is a large language model that accepts speech and audio inputs, responding with text for the S2TIF task, and we enhance it with a VITS TTS model for S2SIF. Qwen2 Audio is a versatile audio understanding model that also performs the S2TIF task, and we build a cascaded system with VITS for S2SIF. Our main results, presented in a table, show that for the S2TIF task, LLaMA-Omni significantly outperforms previous models in content, thanks to its foundation on the advanced LLaMA 3.1 to 8b instruct model. In terms of style, Salmon and others score lower because they are primarily speech-to-text models, often producing formatted content that doesn't fit speech interactions. In contrast, SpeechGPT and LLaMA-Omni achieve higher style scores, with LLaMA-Omni showing excellent alignment with speech interaction scenarios after training on our Instructs 2S200K dataset. For the S2SIF task, LLaMA-Omni again excels in both content and style scores, confirming its effectiveness in addressing user instructions concisely. Additionally, LLaMA-Omni achieves the lowest OSER WER and OSER CER scores, indicating strong alignment between speech and text responses. In comparison, SpeechGPT struggles with this alignment due to its sequential generation process. The cascaded systems, like Salmon plus TTS and Qwen2 Audio plus TTS, also show suboptimal alignment, particularly when generated text includes characters that can't be synthesized into speech. LLaMA-Omni's performance highlights the benefits of generating both text and speech responses simultaneously. Section Summary. In this section, we evaluate LLaMA-Omni's performance on speech-to-text and speech-to-speech instruction following tasks using various metrics, including content and style scores from GPT-4o, speech-text alignment through word and character error rates, and speech quality assessed by the UTMOS score. Our results show that LLaMA-Omni significantly outperforms previous models in both content and style, achieving the best alignment between generated speech and text responses. Section: Trade-off between speech quality and response latency. In this section, we discuss the balance between speech quality and response latency in our model, LLaMA-Omni. This model can generate both text and speech responses at the same time. To facilitate streaming waveform generation, we feed chunks of generated units into the vocoder for speech synthesis once we reach a specific size, which we refer to as omega. By changing omega, we can manage the system's latency. A smaller omega leads to lower latency. If omega is set to infinity, we wait for all units to be generated before synthesizing speech. However, a smaller omega can also affect speech quality, as it breaks the speech into more segments, which might create gaps and reduce coherence. We analyze how different omega settings impact latency, the alignment of speech and text, and the quality of the generated speech. For instance, when omega is set to 10, we achieve a response latency of just 226 milliseconds, which is faster than GPT-4o's average latency of 320 milliseconds, although the speech response may lag by about 1.82 words initially. Conversely, setting omega to infinity increases latency to around 2 seconds. Interestingly, we find that as omega increases, the error rates in our Osser metrics also rise. We suspect this is because the vocoder performs better with shorter sequences, and our Osser model, Whisper Large v3, is robust enough to handle some discontinuities without significantly affecting recognition accuracy. We further assess the naturalness of the generated speech using the UTMOS metric, which indicates that as omega increases, the speech becomes more natural due to fewer discontinuities. Thus, we can adjust omega based on specific needs to balance response latency and speech quality. Next, we present average decoding times for different models on the S2-TIFF and S2-SIF tasks. For S2-TIF, Speech GPT first generates a text instruction and then a text response, while LLaMA-Omni provides concise answers directly, resulting in an average decoding time of just 1.49 seconds. In the S2-SIF task, Speech GPT outputs text and speech responses sequentially, leading to a decoding time about 6 times longer than generating only text. In contrast, LLaMA-Omni generates both responses simultaneously, increasing total generation time by only 1.28 times, showcasing its speed advantage. To illustrate the differences in model responses, we provide an example. We notice that responses from other models tend to be lengthy and include elements unsuitable for speech synthesis. While SpeechGPT's responses are more appropriate for speech interactions, they contain less information. LLaMA-Omni, however, delivers detailed and helpful responses while remaining concise, outperforming previous models in speech interaction scenarios. Finally, we explore the development of speech and audio language models. With the success of language models in natural language processing, researchers are now looking into modeling speech using these frameworks. Early efforts involved training models on audio tokens to generate sound without text. More recent models, like Vol-E and Viola, combine speech and text training for tasks like recognition and synthesis. However, these models do not leverage large language models, LLMs. To utilize LLMs, some studies focus on creating speech-language models based on LLaMA. These can be divided into 2 types. One adds speech tokens to the LLM's vocabulary and continues pre-training with speech and text data, while the other incorporates a speech encoder before the LLM and fine-tunes the model for speech understanding tasks. However, these approaches often lack the ability to generate speech. In contrast, LLaMA-Omni combines both speech understanding and generation capabilities, allowing it to handle general speech instruction following tasks effectively and with lower training costs. Section Summary. In this section, we discuss the trade-off between speech quality and response latency in LLaMA-Omni, where adjusting the chunk size omega allows us to balance lower latency with potential speech coherence issues. We also highlight LLaMA-Omni's efficiency in decoding times compared to other models, demonstrating its ability to generate detailed yet concise responses in speech interaction scenarios. Section: Simultaneous Generation. In this section, we discuss simultaneous generation, which allows us to start producing output before receiving the entire input. This feature is essential for keeping speakers and listeners in sync in situations like speech recognition and simultaneous interpretation. For large language models, incorporating a streaming speech synthesis component can greatly lower the delay between the model and its users. We categorize popular streaming generation methods into three main types: monotonic attention-based methods, CTC-based methods, and transducer-based methods. Monotonic attention-based methods adapt the traditional attention framework to enable streaming generation, using an external module to control the read-write policy, which can be either fixed or adaptive. CTC-based methods introduce a blank symbol in the target vocabulary to signify a wait action. They achieve streaming inference by eliminating adjacent repeated tokens and blank symbols. To combine the benefits of attention-based methods, CTC approaches often utilize a chunk-based non-autoregressive architecture, which has been effective in simultaneous interpretation and streaming speech synthesis. Transducer-based methods aim to connect the non-autoregressive features of CTC methods with the autoregressive dependencies of target tokens. They add a predictor to capture these token dependencies, and their variations have shown strong results in simultaneous interpretation. Recently, we have seen researchers using decoder-only large language models for streaming generation tasks and adapting them into an interruptible duplex model,